All right. Welcome back, everyone. This is the fourth lecture in the sub-series of TQFT talks. I picked this subtitle on the spot. I might change it for the YouTube video, but we're mainly gonna. So we started off with a crash course on category theory on the first one. Second one, we did the symmetric monoidal, braided monoidal functor stuff, and the third one was the cobordism category. And now we're on section 2 of Lucas's notes, basic properties of TQFTs. So we're gonna talk about the classification of all 1D TQFTs. That's why I called it that. But let's begin. So let our Z is our TQFT. This set of data is our TQFT. So we have our symmetric monoidal functor from the category of n-dimensional cobordisms to the category of C vector spaces be our TQFT functor. And we will just, we talked about how the target category can be a bunch of different stuff, bunch of different symmetric monoidal categories, but we'll fix it to be C vector spaces. And we have a natural isomorphism, which is this map epsilon that goes that the functor it's the functor it's a map from the functor applied to our unit in the source category, which in the category of cobordisms, the unit is the empty set, seen as a n-1 dimensional manifold, if you recall from one of our lectures. And C, the field of the vector space is the unit in the target category, and there's a natural iso between them. And so we also have this, yes?
Why do you like to write it as an epsilon? So like you're obviously preferring to map the base field to stuff. Why?
Convention. That's why I wrote it down like that, but I don't know
Yeah.
the source where I took it from, why they wrote it like that. Yeah.
Like usually for like algebras and stuff like that, your unit is always coming from the base field of your thing.
Mhm.
So maybe this is sort of like your Z empty set is going to be the simplest algebra that's going to show up. All of the other unit maps are going to come from C. Okay. This is the only case where you get an iso or something like that. Does that make sense?
Yeah. Yeah. Could be because of that. But yeah. Okay. We also have the map mu that goes from, so remember uh, the the disjoint union is the monoidal product in the category of cobordisms. There's a isomorphism between that and the tensor product is the monoidal unit. Sorry, monoidal product. I think I misspoke here. I meant to say monoidal product in the category of the source in the target category, and this is like the motivation that we began the whole sub-series with, that we want to have this map. Okay, so let this set of data be a TQFT, and M is a closed n-dimensional manifold, n-1, n-1 dim manifold. And so Z assigns to M a linear map. I'll just write down the linear map that goes like this. Epsilon to yes. Okay. In my notes, my empty sets look like phi, so I apologize for that. That's why I need to LaTeX these instead. We were gonna use varphy for diffeomorphisms. That's why. Yeah. Yeah. But thank you for the suggestion. Yeah. It's I always consider that. Yeah. But I think empty set and phi are capital phi are very distinguishable, given assuming the writer writes them correctly. So right. So we were talking that we have our cobordism that starts from the empty set and time, let's say, goes forward to the right and starts ends at the empty set, and our TQFT sends this to C, as we just talked here, and so we'll get a map from C to C. So what is this map? Oh, it's just the map. The endomorphism on C is C. So we have this, and this is the map that Z assigns to M. So I'll just should have written that down, but I'll write it here. The map Z to M. Yes.
Don't you want your M to be an n-dimensional manifold such that -1, because it's the boardism between your two manifolds? You're an n-1 dimensional manifold.
Well, it depends on the again convention. Some texts take board n to be your objects are n-1 dimensional closed manifolds, and your boardisms are n-dimensional. Some take it to be your objects are n-dimensional closed manifolds, and the morphisms are n+1 dimensional coboardisms.
Okay, so either way, the dimension of n is like too small to be of your relevant discourse.
But is this not the object in this that we just said?
But your m is a morphism, empty set to empty set.
My
That's the
M,
point.
oh,
That's the entire
my M is not an object. Thank you. Yes, yes, yes. It's not an object. It's the morphism. It's hom, not object. Yeah. Thank you. Thank you. Thank you. Yeah, I was thinking of sigma, not M. Thank you. And that's good. Okay. So we have this. Now, just right here. This notation denotes a diffeomorphism class. So it's gonna be the notation used was this from so cobordism from the empty set to the empty set, and is a diffeomorphism class of closed n-dimensional manifolds. So now, what does this imply for us? Well, Z induces a that's where induces a manifold invariance. Invariance I sub Z. This is the manifold invariance.
by a manifold.
Diffeomorphism invariant. I should have written this one. I'll end the sentence there and then start a new one. I Z of our manifold being epsilon inverse composed with z manifold composed with epsilon applied to the unit 1. So here I think it'll just be the number 1 in the complex plane. It's going to be in C. So, and this is a definition. I define my this to be that, my manifold invariant to be that. I don't know why I don't have a definition here, but let me define this to be that. Now theorem. And I didn't number this theorem. IZ is an invariant of M under diffeomorphisms. Proof. Bracket M is a diffeomorphism class. QD.
Because by definition,
Yes.
take the board or diffeomorphism.
Exactly. It's I constructed it such a way so that it follows by definition. Yes. Yeah. I
It
just
doesn't make things any easier because your Z has to satisfy this. So constructing the Z is extremely hard, right? Your functor Z has to be constructed in such a way that all of these things are going to be different.
yes.
That's
Yes.
hard.
And so correct. Now correct full stop. Now a separate comment or remark for our subseries. Whenever I talk about uh, uh, diffeos, we always refer to orientation preserving diffeos relative to the boundary that we talked about in one of the lectures. I think in the Bourdism talk, Bourdism category. So whenever we mention diffeos, for our intents and purposes, we only care about uh, orientation preserving diffeos relative to the boundary. Yes. Because right. So this would be invariant under diffeomorphisms, same as this and same as that. So the composition should also follow. It should also be. Yeah. The problematic thing is here, which like by construction, I I said let that be so, and so I construct this thing from with composition, and these things don't are diffeo invariant. So that's why the entire thing will remain like. Okay. Proposition 2.1. Let M and N be oriented closed oriented, and we'll always try to fix an orientation. All of our things are going to be orientable, but not only that, usually oriented. Closed n-dimensional manifolds and Z a TQFT. TQFT then this manifold invariant applied to the disjoint union. It's hard to distinguish between mathcal M and M. Sorry about that. It's going to be M. I think you're going to like the proof for this one. Proof. I should be putting my stuff in boxes because I like putting each element of a talk or notes in boxes, but I imagine these boards are the boxes. Take the boards to be boxes. Until they're not, then I'll put boxes. Right. So, what is this? M and N are objects in our cobordism category. Disjoint union is the monoidal product. Okay, let's draw what that is in our beautiful graphical calculus language that we developed together. Right? And now these are in the category. Now what this notation is telling me is that I'm applying the functor to this category. Now I just move this around, right? Because disjoint union. And by functoriality, I'll explain this more. It'll be this. Oh no, this should be obvious. I remember this doesn't need an explanation. By functoriality is that, and then therefore it is this. Objects in these categories. And remember, in a graphical calculus, when they're next to each other, it means the disjoint union. In the target category, it means the tensor product. And for the algebraic topologists in the audience, this should remind them of the Ekman-Helton type argument. Yeah. So
Yeah,
I see some happy faces.
you didn't mention that you're actually composing. So when they're stacked vertically like that, that's why it's interesting. You're actually going empty set, N to empty set, and then with M to empty set. That's what your vertical stack is.
Yes. Yeah. He gave a talk on that. Yeah. But I think it was in when you proved the Ekman-Helton argument.
Yeah.
Okay. Right. The first one. Let me see. No, this is for the next section. Okay. So let's write it down because this might seem like cheating, but it's not. It's the graphical calculus language that we developed. But let's down the maps. So this is going to be epsilon inverse composed with the z disjoint union of these two. I'm gonna speed through this because we already proved it. Just gonna write down the maps explicitly, so you won't feel like you were cheated out of a proof, but you weren't. So, and this is the composition of gluing of cobordisms that we talked about at some point. So this should be funny a little bit. Apologies for going off the line. So inverse z. Maybe with these things it would be easier if I just like spend more time typing these up in LaTeX and just projecting on the projector and going through it together, kind of like Eduardo does for quantum theory 3.
Yeah,
Probably.
you have to because you're looking at your notes.
Uh huh. Thank you.
Oh,
Yeah, just gonna make it fit. Thank you for that. Okay. So here, right. Sometimes they abbreviate the notation IZ to just Z, but I don't like that notation because Z's are supposed to be our TQFT functor, but whatever. Um, but I think here I didn't do that, so that's good. Maybe here I did, but yes, here I did. It should be I of Z. So expanding this out, by definition, it's this, right? I did nothing, just use the definition for IZ. Here, what did I do? So for this first equality here, view the manifold as a automorphism on the empty set. So what is M or N in this picture? You can think of it as an automorphism on the empty set. You start at a point, and the manifold gives you, in this cobordism category, a map from the empty set to itself. Right. So just imagine the manifold with a point. And so this is having the disjoint union of these is just the composition of these automorphisms. That's why we have this.
because they have no boundary, the composition is the disjoint.
Because they have, yeah, it's closed. They have no boundary. Yes.
Exactly what else
Yeah. Yeah, that's very cool. Yeah. Yeah. And so what did I do here? This is just by functoriality, right? The first time I saw this, I was thinking about it for a long period of time, bashing my head against the wall to try to prove why this equality holds. Then after a very long time, realized, oh, it's a function, it's by functoriality, of course, obviously, duh. And this equality here, I just inputted identity, right? Didn't do anything. And then this last part is just by definition of I sub Z, yes.
There's a subtlety that's not just that. So when you do your IZN, your chain of the things on the last, and then you have the compositions, and you're plugging that in to your chain of epsilon ZM E inverse. So you're not actually plugging into that into that function. You're plugging in IZN. But here's the trick. You know that function's linear. So your IZN is really 1 times IZN. So you can pull out the IZN by linearity. And then you just get 1 left behind, and that gives you the IZN. Small,
1
very
times
small.
IZN, you pull out the IZN,
Yeah.
and
yeah, so like maybe if you just take the left expression
Yep.
and write that as like epsilon inverse ZM epsilon, and then in brackets
mm-hmm,
IZN, because that's what's actually getting plugged in.
yes, mm-hmm,
You're actually plugging in that,
right, because this is the composition.
and you use linearity.
Nice, awesome. Good, and yeah, Eggman-Helton type argument, very nice. I hope that puts a smile on the algebraic topologists' faces. Which things are the same operation?
Circle and cup or whatever prod coprod. We already knew they're the same operation because it's just like by a different reasoning. So we don't use Ekman-Hilton to conclude that they're the same operation. We have like a much more fundamental way of knowing that, just because that's how morphisms are composed.
Yeah. I'm just saying this type of argument, you move this around as a Eggman-Helton type argument.
Yeah. Okay.
Yeah.
Sure. That's nice.
Yes, glad you like it. Yes. Okay, so repeat that again. We have ZM, yeah? Okay.
The M circuit. M circuit.
Sorry, epsilon.
Yeah.
Oh, how does this happen? Right. It's the composition of so so how can you think of a manifold in this setting? You can think of it as an automorphism between the from the empty set to the empty set. Yes, not the point. Yes, the empty set to the empty set. Yes, and now uh, when you because it's a closed manifold, the disjoint union of that is exactly like composing these automorphisms, M and N, right? Can I draw a picture for this? If this is a closed manifold, like a sphere, and I take the disjoint union with like a T2, it's this, right? Now, what is how else can I look at this? M is a um, automorphism from the the empty set to itself, right? In this cobordism picture, it's a map, it's a morphism, right? From this the empty set to itself. Now, if I just and same for n as well. Same for n, the same thing. Now, if I compose this automorphism with this one, I just get this picture.
Maybe draw like little empty set symbols, like to the left and in the middle and to the right, so it's like more clear. It's like a common. So we're going like
Right.
empty to empty. And then
I'm going empty to empty, then again from empty to empty. So the composition of these cobordisms will look like this. And what is this? The disjoint union. Does that make sense? No, no, no. The total space is just M disjoint union N.
maybe also draw a picture of like two compositions where the manifold, the boundary is not empty, to sort of illustrate that like we're thinking of manifolds as being like morphisms between their boundary components. And so like you start with one boundary component and then your manifold kind of traverses to the other boundary component. And so if the next manifold boundary component, like the incoming one, agrees with the outgoing one, you can glue them. And so this gluing is our composition in this category. So if they're closed manifolds, the boundaries are just empty. And so by gluing, we're really putting them beside each other. It could be empty, but like in the case where it's not empty, it's sort of easier to see what's going on. Like if your outgoing boundary for M is the same as the incoming boundary for M, then you can like glue them together. And that's sort of the same as like composing morphisms. So if it were the case that like this common boundary was just the empty set, then the composition is just like juxtaposing them because there's nothing to do.
Yeah. It's like a trivial composition, I guess.
Kind of.
Kind of, yeah.
There's
Yeah.
just no gluing happening.
Yeah, no gluing happening because it's the empty set. Yeah. So yeah, thank you for the suggestion of something that's not closed. So like in the first talk, in the motivating talk, we had that we wanna glue cobordisms together like this, and that we wanted that to correspond to in our cobordism category that is composition of morphisms because this is a morphism right from this to here, right? in our cobordism category. This cobordism is a morphism from here to here, and same for this one from here to there. And when we glue, what are we doing? We're just composing um, morphisms, and that's why we gave this categorical picture to cobordisms. That's why we studied board N as a category. And so, exactly as William said, you're doing the same thing here. It's just you don't have anything to glue, so it's just becomes the disjoint union. Because it's a closed manifold. There's no boundary. Yes.
Yeah, can you explain what this notation is here? Like you have the horizontal MN, vertical MN, and like whether or not they're circles.
Yeah, it's the string diagrams. Yeah. Yeah, there was a whole talk on the graphical calculus. I'm trying to see if I can give a summary. No, it's a very valid question. It's just let me see if I can give a short answer or not. If not, I'll just refer you to the video. So in the graphical calculus picture, imagine time goes upwards and uh, oh, maybe I can tell you to some physics here too, just off the top of my head. And so, right. Mm, yeah, sure. We have something coming in, some object in some category, and then some functor applies to it. You can just think of it as a function taking an input and out as spitting out an output, and same thing happens here. And you can say, I guess there's more to the diagram, but that part doesn't matter. Yeah, you can say I can put this. This is the same as having it like this or like this. Right? Because we took our category to be like this. Now, how can I relate this to physics? Well, if you have a string diagram, maybe not very physicsy, but oh well. Like so. Um,
Not sure if this is a short answer.
that's a good thing. Also, I think what I thought would be clarifying would just be confusing. So I'm gonna not say anything then. Oops, that happens. So yeah, sorry I don't have a short answer for that. What are we doing in time? Oh, 1 hour. Okay. Ah, it's fine. It's fine. I'll pick it up after. But thank you. Yeah, that's true. Okay. I guess over preparing is better than under preparing, I guess. So, definition 2.5, 2.2. Let sigma be an object in our cobordism category. The mapping class group of sigma They don't put this. Never mind. Yes. Is I guess this is a definition, but I didn't put a definition for some reason. But I'm pretty sure this is a definition. Should be a definition. This is the diffuse group or orientation preserving diffeomorphism group mod. The the orientation preserving diffeomorphisms connected components with the identity. And this is isomorphic in this category that it is, whatever category this corresponds to. You can figure that out. To be the connected components of the the orientation preserving diffuse relative to this boundary. Yes. Why didn't I put the plus there? Yes. Yeah. So, yeah, this is the mapping class group. We define it to be that. Now, I define this, define that, and that's the connected components. So, now proposition. Let our TQFT, let Z from our cobordism category to the category of C vector spaces. I didn't even put C here, so I guess general vector spaces over some field. Be a TQFT, and sigma is an object in this cobordism category. Then Z induces an action on the mapping class groups of sigma. Then Z induces an action of the mapping class group of sigma on Z of sigma. Let me write that down. Then Z induces a an action of mapping class group. There shouldn't be a math column, but sigma on Z of sigma. So, well, how does it do this? Okay. The yes. Yes. Yeah, yeah, of course. They're n minus one dimensional closed manifolds for our notation. Different people have different conventions, so whatever it is, it can be differ up to one. So plus minus one.
Yeah. So, and there's the dimension of the
Of the morphisms, and the objects are n minus one dimensional closed manifolds. Yeah. I might get it wrong too because it was funny in the TQFT school. One lecturer used. I think this is more standard than what I just said, and that's why I use it. But the other lecturer right after uses the other notation, so everyone gets confused. So the objects are n minus one dimensional, the morphisms are n dimensional. Yes.
I think that this convention is good because if you take the classifying space of this category, then you get a moduli space of n-dimensional manifolds. So the space of manifolds you get is like the same with the n.
Say that sentence one more time slowly.
So if you take the classifying space of this cobordism category, by work of like Galatius and Randall Williams, you could model this as a moduli space of long manifolds of dimension n. So space of n manifolds, right? Space of n manifolds. It's hard to describe exactly what they are in a few short words, but they're like long with respect to one dimension.
What does long mean here?
Long means that they're contained inside, like, well, they're submanifolds of Rn, and they're contained inside, like, the cylinder in one of the dimensions.
Okay, I see.
Yeah. So picture a long.
Which is counterintuitive because it's very topological and saying long.
Well, the
Yeah.
idea is like you're making them by composing a whole bunch of morphisms.
Right.
So by
A
going
lot of
like,
compositions.
all the way, then it's like you're getting.
I see. But
Is it long like up to diffeomorphism? Because like it's long. That definition like makes me think maybe one diffeomorphism class of a manifold like could be long, but another diffeomorphism class isn't.
Yeah, you can have like some of the manifolds that you'll find can be compact,
Right.
because they're still bounded.
Yeah.
And then other ones will be much longer. And the topology is such that you can actually take like a manifold and like sort of push it away to infinity,
Yeah.
and like pull manifold pieces in infinity, stuff like that. It's a really cool space.
I love these discussions. It's a great place for discussions, right? Got the differential topologists discussing with the algebraic topologists. It's beautiful. But I have a question. Is this a topological group? Because I've only seen the classifying space be defined for on a topological group.
No, you define it for a category.
As well? Okay.
Yeah, you can make a simplicial set called the nerve of the category,
Okay.
where like your p simplices are given by composing like p many morphisms.
Yeah.
P minus one, p plus one.
Yes.
something like
Yes.
that.
Yes.
And then you take the geometric realization of that simplicial set, and that's a topological space. That's your classifying space of your category.
I see. But it need not be a topological group when you take the geometric realization.
No, but if you start with the topological group and you make like your D-looping category with like one object and your morphisms are that group, as long as the group is locally contractible, then the classifying space of that category will give you a classifying space for the group.
That sounds beautiful. I want to see this in detail now.
Yeah.
You gotta.
I can't do that off the top of my
Yeah,
head.
yeah. No, no, no. I know. I just like send me sources so I can read. But that sounds beautiful. Thank you. Yeah, that's nice, nice. The D-looping is a infinity groupoid, no? At least I thought in NLab said something like that. At some point, I went down a rabbit hole and I was like, the D-looping infinity groupoid. And, okay. Went.
As long as G is abelian, it's
Okay.
going to give you an infinity. I don't know if that's a point or it's not, but there's a lot of links between stuff like that.
So just like the loop space applied infinite times, that's what it means. An
Yeah,
infinite
it
loop.
means like you can express it as like the k-fold loop space of something for arbitrarily large k. That's actually the space of the spectrum, I think.
I think Mayuko and Theo like this kind of stuff. Okay, nice. Okay, so how does it do this? Nice. How does it do this proof? Proof that it has this action. Let phi, var phi, be a diffeomorphism from sigma to sigma. Orientation preserving diffeo. So I'll just do this notation, I guess. Yeah, I think this is correct. Please correct me if I'm wrong, but yeah. I hear no objections, so I'll move along. We define the mapping. We define the mapping cylinder. How do you spell cylinders? Yeah, nice. to be continue here. Okay. This is the mapping cylinder. It's last time I put closed 0 to 1, but whenever I write I, it's closed 0 to 1. I'll just define that, so I don't have to write it every time. The closed interval from 0 to 1, and so note that this is a hum from sigma to sigma. This is, I guess, in hum of in the cobordism category from sigma to sigma.
Sorry, is that including one or not? Because the way it's written looks like open.
Oh yes, it was supposed to be a closed bracket. My handwriting is horrible. Sorry. Thank you. Now, we talked about this in the one that we talked the most about cobordisms, whichever talk that corresponds to. That I can do an embedding, a topological embedding from this space to this space. How? Well, I'll just do identity on this one, and this one I shrink it a little bit. I do a bit of scaling. Let's say 1/8, and that's it, right? So what does this look like? When we drew our cobordism pictures, when we were trying to glue them together, and we were talking about smooth structures on like one boundary induces a smooth structure on the entire composition of cobordisms. We had this, and so if you recall, we had pictures that were like this, and we were well, it's just this. We have other cylinders that are half open, half closed, and these get mapped here like this. And another one. So this is a poor sketch, but we already covered this, so this is more of a reminder. So we had this going on. So this is the picture that's going on for what I'm about to write. Sigma cross. This should be from -1 open to 0 closed, right? It's been a while since that talk, so that's why I drew this. It's going to be the diffeo applied to the first one, so there might be some twisting action going on or whatever. It's important for like I don't know if I mentioned, but like the quantum 3 manifold, the quantum invariant of 3 manifolds that Witten had with the surgery theory going on and the knot theory, that also uses this kind of machinery. I might give a talk on that. And 1 plus 1/8 here. Why 1 plus 1/8? Well, for any t, an element in this interval, it sends it to this times t, right? And so at least, by least I mean most left, is going to be what? From here 1/8 to the left, and to t. Oh, that doesn't sound right. Ah, the t has to be here. Yes, yes. The t goes here. Thank you, because that didn't make sense. I briefly went over the calculation and it made sense in my head, but no, I was wrong. Thank you. Okay, so this is the mapping cylinder. Now, the rest of the proof is very cumbersome. I thought to myself that this is the only. I thought of not providing a proof at all, but I don't think it just takes a lot of time. But I thought this part of the proof is good to know.
Yeah, it's helpful to remember that like our things aren't just Fordisms, but we also have these choices of colors.
Yes.
So that we're able to group things with having like a compatible structure.
Exactly. Once we added the smooth structure, that's when we cared about like the colors to glue stuff and to have a compatible smooth structure on the entire thing, induced by having a smooth structure on like one of our objects or morphisms. Yeah.
It's hard to imagine that this like action is not trivial because it doesn't do anything topological. I guess
Yeah.
that's what's interesting.
Yeah, because, well, yes, that's
Well, I guess there's like a twist.
I was just about to say the twist. Yeah, the twist that matters for the like smoothness stuff, but topologically, yeah, it's trivial as you said. I can't imagine it not being trivial. I'm pretty sure it's trivial. The reason why we did this whole collar embedding thing was because of the smooth stuff to see how we actually I think provided in explicitly how it induces the smooth structure canonically, but I think we did that.
And I think like topologically it's still gonna be interesting because if you think about like variance on either of the cylinder,
Mhm.
like you're still getting a non-trivial map between those groups induced by the diffeomorphism phi. So it's not like nothing is happening. It's just that you just have a cylinder
Mhm.
topologically, but like still some like non-trivial process going from one to the other, controlled by this phi. So
Yes.
once you glue on another cylinder,
Mhm.
it's going to kind of twist you into.
Yes. That is true, but is that topologically significant?
Like it'll be detected on the topological invariants. But like the boardism, the
Mhm.
space that the boardism represents is just a cylinder. But like how Z is going to transfer information from the left side to the right side
Yes.
being picked up
Yeah.
by stuff.
Yeah. Yeah. If you forget all the smooth structures stuff, all that information, just think of it as like a topological boardism, then yeah, it's nothing special. But yeah, when you have
I still think it is. Like it's just whatever the Z is doing. Like it's going to detect whatever phi is doing to the topology of sigma. It doesn't matter like smooth structure or not. Like there's still phi is going to do stuff on homology, right? And so your Z, as long as your functor Z is sufficiently interesting, that's going to be like detected on the morphism going from the left side of this mapping cylinder to the right side of this mapping cylinder. Like it's not like a purely smooth thing.
you mean not a purely topological thing.
I mean, it's kind
Yeah.
of both because you can have
Yeah.
diffeomorphisms that are topologically trivial, but you can have topologically non-trivial diffeomorphisms. Like this is something that like this is going to detect topological stuff,
Mm-hmm.
but also some smooth stuff.
Mm.
So that's good.
Well,
It's
what
less trivial than it looks.
I see. I see. What's an example of a topologically non-trivial diffeo?
It's a good example of this like stuff that you can use to construct like exotic spheres.
Mm.
Like you can have diffeomorphisms of the sphere which are homotopic but not isotopic.
Can you define isotopy?
It's a homotopy through diffeomorphisms. It's
Ah,
a path in the space of
of
diffeomorphisms.
diffeomorphisms, right?
So this is like one of the manifestations of exotic spheres is the existence of these functions that are
Yeah.
homotopic but not diffeotopic.
Yeah.
So I think that type of thing could be picked up by a sufficiently well chosen Z. But like more generally, they are going to detect the topological effects of phi on the topological variance of whatever sigma.
Right.
Yeah, I don't want to like
Yeah.
keep harping on.
I don't know. I
Yeah.
enjoyed it. Nice. Yes. Awesome. All right. Yeah. The rest of it, I'm just gonna not do. Yeah. So because we have better stuff to cover. And that better stuff is dimensional reductions. So let our I'm not gonna write this. I already wrote it there. Z is a function from Borden to vect, a TQFT, not just any function. And so let sigma, sorry, omega be an oriented closed k less than m dimensional manifold. Yeah. Now, the dimensional reduction of Z along omega is the n minus k dimensional manifold. So TQFT. There we go. I was like, what is going on? TQFT. That there should be a comma there. We denote the dimensional reduction of Z along omega as red Z sub omega, or red sub omega Z, going from a n minus k dimensional cobordism to a n dimensional cobordism to vect. How does it do this? Well, this map is just RZ. Now, can anyone think of some map that gives you this? You don't have to. I mean, I'm defining it, so I'm supposed to say what it is, but I want to see if you can give a creative guess. Yes. Yeah. Thank you. Exactly. So yeah, this is n minus k. The objects are n minus k dimensional, right? No. The bordisms are n minus k dimensional. Multiplied by omega, you get n dimensional cobordisms. Yes.
So if you wanted to like study physics or something where everything has like a circle factor, then you would do a dimensional reduction along the circle or something.
What is a circle factor?
I don't know. I'm just wondering like when would you want to do it? This is the
Ah,
serious question.
oh, that'll be answered. So here is m goes from sigma to sigma, right? And this is this map. And so this gives me m times sigma. So omega. Oh my. Goes from sigma cross omega to some different sigma times omega. Exactly what you said. In particular, for all sigma, there exists a 1D TQFT. Reduction of Z along that sigma goes from 1D cobordisms to vect, such that when you apply this to a point, you get your TQFT applied to sigma. I'll write this down, don't worry. So what does this imply for us? That if understanding 1D TQFTs has implications for all other TQFTs, all TQFTs of other dimensions. So if we're using this dimensional reduction, we can just start studying 1D TQFTs, and that'll give us a lot of info about TQFTs in higher dimensions. And so let me just write down what I wrote, what I said. But I wanted to say, this is one way of doing this. More complicated way of doing this is just like having some kind of vibration. Like you have a like omega fibered over m.
Take a circle bundle associated to the tangent bundle somehow, something like that.
That's an example, yeah. And but this is the easiest one I've seen. And now, so this might not always there might not always exist this map such that for any arbitrary Bordism here you can do this dimensional reduction, right? It doesn't work for any arbitrary TQ n dimensional TQFTs.
Are you just like precomposing the functor? Doesn't that just give you a new functor?
Precomposing with a functor. Oh no, I'm saying that what I'm trying to say. Let me think about what I'm trying to say while writing down this. Okay. In for all sigma, I'm not gonna write in board and objects in board, and we already said that there exists. Oh. That was a different thing. There exists, right, a 1D TQFT PT denotes point. This is a oriented point. I'll just give it the orientation plus. Okay. So we have this dimensional reduction. Now, for the specific case of take k to be n minus 1, you get a dimensional reduction of z along sigma. You get a 1D TQFT, this, that goes from board 1 to vect. such that when you apply it to a oriented point, you get this. Now, so having this, we can study this 1D TQFT, and we'll be able to gain knowledge about higher dimensional TQFTs. Now, that part will come in subsequent talks. Not this one. Yes.
That to work, you have to like know about the n-dimensional. If you want to know about n+1 dimension, you have to know about 1 dimension and n dimension, basically.
I don't know if have is the right verb. Maybe can.
It's good to know.
Good to know, maybe.
If you want to know what's going on with this, you're reducing. But I guess it's not clear what's going on with you already know this like omega, right? Or am I-
Yeah, no. I think that's true, but I'm not certain. I think this what it's trying to be is maybe a specific case or an implication of the cobordism hypothesis, but I haven't gotten to studying that rigorously yet myself. So, um, I don't have great insight into it. But this will come up later. We'll do this. We'll actually see what kind of information we can gather for the higher dimensional TQFTs from the 1D TQFTs. Yeah. So I guess we'll see that later. I guess I can say that. We'll see that later. Okay. How are we doing in time? It's 6 p.m. Okay. We started near 5, but okay. So, lemma. Lemma slash fact. Why do some people use fact for their notes? Well, if they don't want to prove something, then you put fact. And that's why, oh, that's a nice 2. That's why I'm putting fact. Every connected compact oriented 1D manifold is diffeomorphic to S1 or the interval.
Does it have to be oriented?
Yes. That's true.
You can choose orientation. That's one of the
Yeah. Yeah. This is still correct, but we can state a more general one. Just cross this out. I don't know why they mentioned orientedness. Still not wrong, but yeah.
Are no non-oriented.
Yeah, but need not be oriented.
Yeah.
Orientable, yes, but not oriented. But yeah, that's true. That's true. There does not exist non-orientable ones. Yeah. Very good. I love classifying topological spaces of different dimensions. So, another fact. And so this is obvious to see. That's why we're not going to prove it, right? every 1D cobordism is a disjoint union. I hope I wrote that correctly. Of its connected components. That is true. Yeah. Optional. But yeah, that is true. I don't know why they put that then. I didn't even think about, but obviously, yeah. Good. Good thing is that it's not wrong, right? So for this part, I have to admit the plus minus signs, how they induce an orientation on the cobordism, I really didn't understand. Still trying to figure that out myself. So, because I thought the rule with this would be that it goes out from this plus and into the minus, but that doesn't seem to be true all the time. So, I'm confused about this. If anyone knows, let me know. I'll try to figure it out if I can at some point. This is the braiding. Sigma is the braiding that we talked about. So you can, these are the same up to braiding. Sigma, you have plus, minus, minus, plus. So these are everything that we have in 1D. It's even less than this. Just having these two and these two is enough because these are related via braiding. Yeah. The intervals you have here, these two correspond to the interval. And if you want to make S1, you just compose, for instance, these two, and you get S1. Yeah, these two because the orientation is compatible as well. So it's only these two and these two. And this classifies all of this, yes.
Like, how does the braiding work in this? Is this how we're defining the braiding, or have we already have a braiding on this category somewhere that I don't remember? This is how it works in this case.
Well, so our functor is a symmetric monoidal functor. That means that both the target and the source are symmetric monoidal categories.
Not braiding.
Not braiding. Or trivial braiding. But if you symmetrize the braiding. Yeah. Yeah. So as in like we don't see braiding. And
So this is just the symmetric structure.
yeah.
Where is it going from? Where is it going to?
Oh, as like a functor or natural transformation, you mean? Yeah. Well, these are morphisms, so it's a functor from that to that, and it's just like it identifies them. Yeah, it's a natural transformation on the functor of the monoidal functor, tensor product. But that's what it was in the talk. So here, trying to relate the two, because you're right. In the talk, we have our monoidal functor, the tensor product, and then we have this natural transformation of braiding, and we symmetrize it. No, oh, uh, here it goes from the disjoint. So
So it'll be like
no.
C plus tensor C minus dual, and then you're swapping those two around, getting something.
So okay, wait. Here it goes from the disjoint union of 2 points to the empty set. This is the morphism. Yeah, this is the morphism. It goes from the disjoint union of 2 points to the empty set.
Swap.
Yes.
Oh,
Oh, so yeah,
okay.
very nice.
Okay.
That works. I'm glad we worked that out. Nice. Awesome. No, thank you for the good question. Yeah.
I forgot what direction.
Yeah. Well, yeah. Because a lot of the graphical calculus we wrote was from down up, but here is left to right. Those are the usual like time orientations in the string diagram graphical calculus stuff. But yeah, yeah. Okay, so it's good to work these out. It is a learning seminar after all, so it's better than just me throwing facts at you and sometimes proofs. So a one-dimensional TQFT is completely determined by some data, which has to satisfy some condition. So let's now talk about these conditions. So I'll just leave that as a verbal remark and then talk about the conditions. Do you know about the Freed-Hopkins map?
I've probably seen it.
Mm,
Where does
yeah.
it go to?
I forgot now.
Space interpretation of invertible TQFTs?
I think so.
Probably seen it.
I saw it in some some extended TQFTs, invertible TQFT stuff.
Something about an N.
Yeah, something. We'll probably get to that at some point. I want to do the model categories, fiber categories, infinity and infinity categories, and infinity groupoids stuff. I also wanted to do obstruction theory at some point. We'll have to learn it properly. Still have absolutely no intuition for BO or BSO.
Classify one?
But then take the co-limit. I was saying BSO, not BSON.
Classify stable.
Yeah. But that's words. K theory. You just threw 2 words at me. Not even a sentence.
Give me like 3 talks about K-theory.
Yeah, but like threw 3 words at me. 2 words, not even a sentence. That doesn't really explain much, but I love that. Okay. Okay. So z of a point that has plus orientation has to be this vector space. So I guess I'm assigning this to it. These are the conditions that I want it to satisfy. Same for the negative orientation. For a point, I want it to be, and these are vector spaces, right? Objects in the category of the target category are vector spaces of our TQFT functor. So, what else? Z of this goes from V plus tensor V minus to C. And so yeah, this is where that braiding that I mentioned happens that we figured out. And Z of other way around goes from v minus tensor v plus to c from that. Yeah. C to that. Okay. Example. Finally, an example, right? Example, I have this. Okay. I have this. So, what is this? I'm going to write it there. Z, our functor applied to, our TQFT applied to the disjoint union of these 3 points. Well, the disjoint union of the image of the TQFT on the disjoint union of this is going to be, well, V plus tensor V minus tensor V plus. We just said here, right? Plus plus minus. Uh-huh. Yeah, wow, why did I put minus there? Yeah, that's a typo. Yes, it's correct in the notes. Okay, now I use the braiding. So the first one I don't do anything, second one no, not braiding yet. Sorry, not yet. That's the next step. I jumped a step. So I'm gonna do the cap there, or co-cap, or whichever it is, of this. And this is just gonna give me V plus, right? Because that's gonna be C. V plus is just V plus, right? And now, so right now, where am I at? I'm here in time, right? From left to right. Now I want to do a co-cap or cap or whichever it is, whichever cup. Yeah. Some people call it cap. I don't know.
If it was like up and down,
Oh,
it's like
cap,
a
co-cap.
C.
Fair. Whatever you want to call it, that thing. So on the this still identity, right? Nothing is happening to this one, but this one, something new is emerging, and that new thing being tensor functor on this, right? And so we already said what this is. It's going to be tensor v minus tensor v plus. Right? Okay. Now I have to put the co-cap, right? But imagine I didn't have these two here. So sorry, apologies to the cameraman, but yeah. So imagine if I get rid of these two, because I said it's not necessary, it's a bit redundant, these two. And I just have these two because these are related with the braiding. So let me get rid of these two for a second. And if I have just two, going back to the picture, sorry. I'll wait for the camera to. So the orientation that I have now, what's going on with the orientation? The orientation here is counterclockwise for this piece, right? For this co-cap. But for this cap, the orientation is clockwise. So I have mismatch orientations. What do? I use the braiding, right? And why can I do this? Well, geometrically, what this is telling me is that this is the exact same thing as this, as a topological manifold not embedded in any higher dimensional manifold, right?
Put the arrow on the other side.
Thank you, yes. And so it's not a manifold embedded in a higher dimensional manifold, just a manifold. These are the same thing, right? Twisting it doesn't do anything. So what is this? Okay. Now, if I do act on it with identity times sigma, it's going to swap these. Give me v plus tensor v plus tensor v minus, right? And now I can act on it with the cocap. Now the orientations are going to match because the cocap goes from where? V plus v minus tensor v minus. So now I can act on that. I couldn't act on this because it was the wrong orientation, but now I can do it. So this is gonna be identity. Let's see. Whoa.
Yeah, I just want to draw that.
Whoa. 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 There we go. Right?
Should be circled. Yeah, I guess so.
Yes. Definitely should be circled. There's a typo in my notes then. Yeah. Yeah. Okay. This this gives me what? Just v plus. There we go. We actually computed a TQFT functor.
Well, I guess you didn't
Yeah.
specify anything. How do you know you can find?
This is already too concrete. It's concrete enough. It's too concrete. It's like doing what you're asking. This is already physics. That's even like more concrete than physics. The Picard groupoid, the Picard infinity groupoid.
Yeah, is that
I don't know.
is that too physics?
Maybe, but like I don't know how you would do that with the Picard infinity groupoid. I barely know the definition of the Picard infinity groupoid. I don't even remember it.
Still, like any invertible TQFT has the fact one where all of the values are one dimensional. You need all of your values to be like invertible in your vector space category.
Yes.
The way you can do that is if it's like
A group.
graded line.
Mm.
Yeah.
Yeah.
So if your V's were one-dimensional complex vector spaces, you could construct an example where everything is just complex numbers, and all of this stuff is just numbers.
Yes. Yeah. That's very true. Yeah.
But choosing not to write down a definition like a single TQFT, you're just telling us that
Yeah. Yes, I am doing that.
Sure.
Yeah.
That's fair. I'll do it.
Yeah. Good. I'll leave the concrete examples to the physicists.
Mike Hopkins as well.
And Mike Hopkins, yeah. And whatever Witten corresponds to. Whatever category Witten is an object in. Oh, did I finish? Yeah, okay. How are we doing on time? Yeah. Worst case in 5, so okay. Oh, I'm almost done anyways. Yeah, I didn't prepare too much. Too much. Okay, I think we can, yeah. Cool. Okay. Yeah, okay, we got this. Exercise. Convince yourself that all relations are generated by the following two relations. Exercise. Convince yourself all relations are generated by the following two by I'll just write it down by these. Oh, you're saying in equality, in what category is this equality in? Yes. Yeah, in our morphism category. Yeah, cobordism.
I have like a more general question.
Yes.
So if you drew a diagram,
Yeah.
obviously one of the things is closed manifold. Whatever, like suppose like the both ends were complex plane or whatever, or even no, you just get a morphism from the left to the right. So if you had not included that closed manifold and computed the morphism, is the answer with the manifold included just multiplying by
Yes.
z of that manifold?
Yes. And the z of the manifold for a closed manifold is what? Is going to be c, right? Because
No, it's not c. It's just a complex number. Exactly. Yeah.
yeah,
It's just scaling
so
whatever
an element of c. That's what. Yeah.
I'm saying like you have a
You scale.
morphism, you just scale it by you drop in closed manifolds and then scale by their c value.
Yes. Exactly.
Okay.
Exactly. Yeah. The picture that we drew at some point mapped from C to C, which is C.
What does that mean in like a physical system?
I don't care about physics.
Like was it anion braided?
Oh my god, talk about anions. I loved Witten's TQFT and Chern-Simons Witten theory talk. Also love how he refers to himself, to his own theories. Whenever it's his own name, he just doesn't say it. He abbreviates it to W. So like for Chern-Simons Witten, he just says Chern-Simons, or yeah. Very humble guy. And but why did I mention that? Oh, he talked about anions there. Didn't understand any of it. Didn't care anyways. Care about higher category theory. We still need to define the infinity topoi of the infinity stackoid, whatever that is. I don't know why I'm mentioning these things for the talk. Lemma. Yeah, convince yourself of this. So the category of 1D TQFTs is equivalent to the category of to the category with objects with object right here, a pair of vector spaces, vect spaces v plus and v minus, and linear maps v plus evaluation and co-evaluation. if you take, I think Faisal's non-commutative algebra slash rep theory, um, I believe in that. He defines the trace in a way more general setting. And I recently saw the trace being defined just using co-evaluations and evaluations in a braided monoidal category, and it was beautiful. It's beautiful seeing going from the physicist's way of thinking about trace to that, and it's even more insightful in ways when you do like tensor modular tensor categories. It just corresponds to creating a circle out of in your graphical calculus when you have objects goes out. The trace is just this at the top.
Or whatever. Yeah, just you have to like braid for you the evaluation, right?
Braid with what?
The braiding, the sigma,
Yeah.
right? So you have your co-evaluation at the bottom. You apply your thing.
Yes.
Then you want to evaluate, but you can't. You have to braid first.
To evaluate.
For the same reason
Yes.
as we had over here. So
Yeah.
your string diagram needs to have a little half twist at the top corresponding to the braiding.
Yeah. Yeah.
In order to do it like completely correct.
Yes. Yeah, I guess I saw it in the symmetric setting where they didn't care about that. But yeah, you're right.
Yeah, we did it like,
To do a like evaluation, co-evaluation, you need to fix the thing by doing a braid. Yes.
we did it in like the PMAP quantum info course. So I guess they care more.
Did you take it in Bezos here?
I don't think so. I took it with Roberto.
Oh, okay.
I took it with Dan.
I see.
He wasn't bad.
I see. Yeah. When Basil took it, it was a special topics course, so they went more crazy with that course. But yeah, a lot of the things, like if you take that course and then you do like, there's like symmetric monoidal categories, evaluations, co-evaluations, maybe dual categories. You realize, oh, it's like it's just what we did, but fancier. Yeah, in the quantum info course, yeah. Still shouldn't be called quantum info. It's really not quantum info. No quantum information theorist would ever call that quantum info. It's lineage 3. Yeah. Yeah. What's the word? Rebuke? Rebuke that, yeah. Anyways, we have, where am I? Wrong board. Here. We have evaluation and co-evaluation such that, just erase these. So, such that if I start out with a V plus, and remember in the, actually, never mind. Not gonna mention it. Evaluation, and then co-evaluation. This goes to V plus. This is the same as just having V plus do nothing to it, right? I'm gonna call this 2.1. We're gonna use this later, like refer back to this equation. And the same thing, but other way. Two point two, hold. And these are the objects. Morphisms. are given by pairs of maps eta plus from v plus to v plus prime, and same thing with the negative, v minus to v minus prime, and such that we have the following diagrams. Call this 2.3 because we're gonna refer back to this for other condition, for satisfying this condition later on. It's gonna be minus eta plus v minus prime, right? It's gonna be in the prime category. Good thing we do know that graphical calculus, it helps us here for making the proofs faster. I mean, that was the whole point, right? So obviously it would defeat the purpose if it didn't. Yes. Yes.
Is there any way to use this structure to see that maybe V minus has to be isomorphic to the dual of V plus or something like that?
Is there any way structure to prove that V minus has to be isomorphic to what?
To the dual of V plus.
Oh, dual of V plus. We'll get to dual categories in a second. It's the thing right after this. But
True. Or do they have to be limited that way through these co-evaluation maps? Or can they just be random, pretty much random vector spaces?
well, I think for that, it's general vector spaces. It can be random vector spaces, but let me do the. Let me talk about dual categories, and if it doesn't answer your question, ask me again.
Okay.
Because it's the thing after this. And since you asked about dual categories, I'll wait till there. So now the proof of this. Well, the proof of this, what I have written down, is that. Oh, let's just. I think we should just write it. Proof. Objects are obvious. How is it obvious? Let's see. The category of 1D TQFTs is equivalent to the category with objects those, and morphisms are those. Yeah, I mean,
Given a TQFT.
yeah, the TQFT, yeah. Okay, so that's good. Now, objects are obvious. Let me fix my M here. That's what Lucas gave as the proof. He said objects are obvious, so yeah. And I'm following his stuff very closely. So, morphisms. Morphisms eta from z to z prime is fixed by its values on the plus minus points, which we call eta plus and eta minus. Now, for these to be natural, it's just enough that to check the diagram for generating the morphisms are exactly 2.3 and 2.4. So what are these diagrams then? Well, applied to, you know what, I'm gonna change the notation midway through the talk, horrible idea, but point where positively oriented point to z prime of and eta minus does the similar thing. Not gonna write it down, it's just minus. And we want this diagram to commute z of sigma through eta of sigma gives me z prime on sigma. And what is my z of m having this cobordism here give me? Well, m is going to take sigma to sigma prime, and this bifunctoriality, you can bring this inside of this functor and becomes sigma prime. So this becomes z of sigma prime, and then this eta of sigma prime acting on sigma prime, this gives me a z prime of sigma prime, and this is just z prime of m. This commutes. And it says plug in the generating morphisms. That's a great question.
Are we constructing a functor from the category of 1D TQFT?
To prove the equivalence?
Or are we going the other way?
I don't know, let's figure it out. So the claim is that category 1D TQFTs is equivalent to the category that has objects. The objects part, we just gotta check the objects and category and morphisms are the same. The objects are obvious, right? Morphisms, however.
Not like checking that they're the same. We're constructing the functor from one to the other and have to show that
It's the natural iso.
fully faithful,
Fully
essentially surjective. That's what a equivalence of
Fully
categories
fully faithful and subjective. Yeah.
essentially surjective.
What's that?
Meaning that everything in the image is isomorphic, or sorry, everything in the target category is isomorphic to something in the image. So if you think in terms of a space, like it just means it's surjective on pi 0.
It's if I think of a space.
If you try
Um,
to like press your intuition for a category
yeah.
down to space land,
Yeah.
essentially surjective kind of means that you're like surjective on pi 0. Everything in the target space you can connect to something in the image by some path. And then in a category sense, this path has to be an isomorphism.
I see.
Surjective.
I see.
So that's what an equivalence of categories is that it's a bijection of all the Hom sets, and that everything in the image is isomorphic to something. So everything in the codomain is isomorphic to something in the image.
Yes.
Yeah.
I see.
So we have to construct a functor, which is what we've done. Given a TQFT,
Yes.
we're like, okay, we get these vector spaces by definition.
Yep.
That's what sequence gives them to us.
Exactly.
Get these co-evaluation maps because we apply them to our co-cap and our cap objects, or morphisms rather. And so that's where we get the data for the object. So now we need to start with morphism in the TQFT category, which is a natural transformation eta. And we have to come up with one of these etas, a pair of maps, eta plus and eta minus. So this diagram, by assumption, commutes because we're assuming that eta is a natural transformation.
Yes.
So we need to know that the eta plus and eta minus
Is a natural.
satisfy these diagrams here.
Aha.
so that they actually are a morphism category.
In our new in the category of TQFTs,
Yeah.
which is a three morphism in the entire thing. Yeah,
So
it's
this
a
is
natural.
what we have to do to show that the functor is defined. And on top of that, show that it's fully faithful and essentially surjective.
Uh-huh. Okay, so for this,
Yeah. So
for
we've got
that, we
So we've written down our eta plus and eta minus. It's just like, what does eta do between our two TQFTs? So we have those, we just have to show that your evaluation, co-evaluation
Mhm.
rules are satisfied.
exactly to show those are satisfied. Yeah.
So you have to have a map from B plus tensor B minus, then you apply eta plus and eta minus to the coordinates, then you do eval prime. So try doing that, see if you get